Welcome back. This video is on test of independence. Let's start with some definitions. A contingency table or a two-way table relates two categories of data. The marginals or marginal distribution is a frequency or relative frequency, remember relative means percent, distribution of either the row or the column variables. So these are pretty much the totals. The conditional distribution lists the relative frequency for each cell. A test of independence is once again a hypothesis test. So the test of independence tests the null hypothesis that in a contingency table, the row and column variables are independent. So once again, we're going to see some familiar for observed and the expected for O and E, like we saw in goodness of fit. R, lowercase r, represents the number of rows in a contingency table, not including the labels or the rows, or the totals. And then C represents the columns in the contingency table, and again, for just the data. The requirements, as we always see with hypothesis testing, must be random. We see that every single time. The sample data is represented as counts, so not percentages. For every cell, the expected frequency is at least 5. There is no requirement that every observed. So this is kind of similar to what we saw again for goodness of fit for the requirements. So our hypotheses are going to be the row and column for our null are independent, and our alternative is going to be that they are dependent. Now, I don't want you to say that. I want you to relate it back to it. So you could say, you know, gender is independent of height, or gender is dependent on height, something like that. So I want you to, this is more generalized, but I want you to actually say what it's about. Here's our test statistic. That should look familiar, kind of like with goodness of fit. And this time our E, our expected, is the row column, the row total, the column total, and the grand total. Now I'm not going to make you do the expecteds by hand. Our calculator will do that for us. But if you do want to check it out, then you could do that as well. We're going to be using, of course, our calculator, so we're going to be using p-value method. Let's look at number 4. In a test of effectiveness of echinacea in recovering from a cold, some test subjects were treated with echinacea with 20% ethanol, some were treated with echinacea with 60% ethanol, and others were given a placebo. All of the test subjects were then exposed to rhinovirus. Results are summarized below. Use a 0.05 significance level to test the claim that getting an infection is independent of the treatment group. What does the result tell us about the effectiveness of echinacea for colds? So notice I don't have my columns here, my totals here, but I actually don't need it when we're going to plug it in. Now if I go to my calculator, let's first go to stat and test and push up. And here's my chi-squared test. If I hit on that, then I see this. And that should key me in that I'm not just doing L1 and L2. So normally we would do L1 and L2, but if we look back at our data, I can't really do L1, L2, L3, or we don't want to put it in that way. Instead, what we're going to do, we're going to go to matrix. If you look at matrix underneath that x to the -1, you see a little matrix sign. Push second matrix. And you'll see mine, yours is probably empty, or you might have something different. Go ahead and push over to edit, and push 2, enter, 3, enter, and then you're going to start filling in. Mine's already filled out, so you can pause it and fill it in, but if you just hit 88, enter, and so on, 48, enter, it'll keep on going to the next one. Okay, so that's how we plug it into the calculator. So let's go back to here. Our parameters are going to be, we're just going to say, it's not really a parameter in the sense that we've done before, so we're going to say parameter are infected or not versus echinacea placebo. And there's levels. There's a couple, 2 extracts. But we're just going to say something like that, and we're testing independence. Or you'll see if the question says, is there an association? That's the same thing. All right, so that's our P. H, state our hypotheses. So remember that your null should always say no difference, no change, no association. So our hypotheses is going to say there's no association between treatment and infection, which means that it's independent. So getting the infection that they exposed them to, or virus that they exposed, the virus they exposed them to, is independent. They don't have anything to do with each other. This one would say there is an association between treatment, which is the echinacea treatment, and infection, which means somehow they do depend on each other. So that would tell us that that they are dependent and that there is an association. So echinacea may be helpful with helping us preventing getting a cold. Show the assumptions. Random. Did it say random? Let's look back up. In recovering from a cold, all the test subjects, it doesn't say anything about being random. So let's go down here and say random doesn't say, so we're going to proceed with caution. But we would write that at the end of our statement and kind of say, if we were running a test for someone and say, these are our reservations with this, it doesn't say, or we would report back to the company that was hiring us and say, can you tell me how you got this data? The different categories, we see that there's 2 categories for infected or not, and then 3 categories for the treatment, which means there was 1 what was placebo, and then 2 had different strains, different extracts of the echinacea. The expected count's at least 5. For this, since we're not doing it by hand, we're actually going to run the test right now, and then we'll come back to this and write this in here. So let's go ahead and run the test, and then we'll be able to do the rest of ours as well. Let's go to our calculators. And we have this already in here, the 2 by 3. And now let's go back to stat test and up to chi-squared test. And we had already, whoa, that's not what I wanted. Stat test, chi-squared test. So my observed, we punched in. Notice that expected will always stay B. Go down to calculate, or we can go to draw. Actually, let's go to draw. And let's go here. That's a pretty big area, right? So we see that because of the number, the degrees of freedom aren't very high because there was not a lot of categories, but I can see a lot is shaded here, so I can see that's giving me a pretty big p-value, and there's my test statistic. So I'm going to use that in a minute, but let's go back to matrix. So second matrix. If you didn't have this before, you do now. So notice that that was probably blank for you, and now there's a 2 by 3 that's matching it. Let's hit enter on there. And it looks like that. See how it's kind of like cut off there. So let's go to see it better, let's go to second matrix and down to number 2. And if I go to edit number 2, then I see it a little bit more compact. This is my expected. So once I ran the test, these are my expected values here. Now I needed all of my all of them to be above 5 to match for the assumptions. So what we're going to do here is we're going to write this down. So I'm going to make this a little bit smaller here. And let's go here. I'm going to move this over. And under my assumptions, we did the random, we talked about the categories, the expected counts at least 5. Let's say expected equals, and I'm going to pretty much write this matrix here. So 88.57. Okay, expected counts at least 5, and I can see they're all cells have greater than or equal to 5. So this is checked off as well. But I want to see these counts. It also shows me that you ran the test correctly because I can see those as well, and all the cells have at least 5. So that's how we check that. Now we could do that by hand, but I'm just going to let you be able to use your calculator for that. All right, so name of our test is a chi-squared test. You can just leave it like that because that's your that's what the calculator says. If you want to be more clear, you can say chi-squared test of independence. But if you just say chi-squared test, I'll take that as well. Test statistic and p-value. Now I want to go back to my calculator again. I had to get this for this, so I wanted to go back to stat test and then do my chi-squared test. It's still in there, but I need to see the 2 values again because I did not write those down. All right, so my test statistic is chi-squared equals 2.9255, and obtain my p-value. My p-value was 0.2316. It's a very steep right skew. So I'm going to say that this is my test statistic, chi-squared equals 2.9255, and this area is 0.2316. Probably could have gone a little bit further because there was a lot of area there. We said there's a lot of area there, so there's a high chance this would have happened, and not just by chance. So our decision, our 0.2316, is greater than 0.05, which is my alpha. And so we are going to fail to reject. The null. So for my summary, if you need to go back and look and see what our null was, but it was that they are independent of each other. So if I go back, there's no difference, so there's no association is what we're saying for this. So my statement is there is not sufficient evidence to say that getting an infection or virus, whatever it was up there, so there is not enough evidence to say that getting an infection virus is dependent on echinacea, on treatment of echinacea. So if it's not dependent, then we would say that that echinacea is not, it's saying that it's not effective. It's not making a difference whether or not you get a cold. So number 5, suppose a sociologist wishes to see whether the number of years at college a person has completed is related or associated with his or her place of residence. A sample of 88 people is selected and classified as shown. Notice it doesn't say random, so we're going to have to address that in our assumptions, but I still want you to run the test. Now you have this. And it gives us the totals, which is really helpful when we're doing probability. But when we're trying to run a test of independence, the only thing we're going to plug in is this into our matrix. So notice that it's 3 rows by 3 columns. So we're going to make our A a 3 by 3 matrix. Pause this video, go into there, and make that matrix. Alright, so in our thing, if I went, mine's already in here and hopefully yours is too. Notice now mine says 3 by 3 and then 2 by 3 because that's still what the expected was from my last time. Now when I run the test, it's going to change that to match this. So it is going to change that there. We know we're going to need to run the test so we can see the expected. So let's go ahead and go to stat test and up to chi-squared test. And let's go to calculate just to see how that comes out. I'm going to need this later, right? And you can write that down somewhere if you want to. But let's go ahead and go to second matrix. And notice now that my 3 by 3 is there. So my 3 by 3 is there, and I can edit it. So edit down to number 2, and I can see this. My expected counts are all above 5. That lower one is barely above 5, but it still counts. It's still satisfying that. They didn't say random, so remember we are still going to have to address that in here. All right, so let's go ahead and start our hypothesis test. So we're doing phantoms. So our P, our parameter, as we're saying, we're doing location versus number of years of college. And we're doing independence or association. My hypotheses, my null, is going to be saying independence. So we're going to say a person's place of residence is independent of the number of years of college completed, which means that it doesn't matter how many years of college I completed based on where my residence. So it doesn't matter of where I'm living because of that. My alternative is going to be the exact same thing, but it's going to be dependent. A person's place of residence So a person's place of residence is dependent on the number of years of college completed. I'm doing a little more of this. Hopefully you guys can take up a little more room this way so you're not writing so vertically, because I want to keep this up for what we're doing next. So A, our assumptions. Random, doesn't say. So proceed with caution. Or more likely we would check with the person that we're running the test for and make sure that it was all on the up and up. The categories. there were 3 categories for location and then 3 categories for degree. So 3 categories for location, 3 for degree or years, and the last one is the expected counts. And remember, I want you to, so greater than or equal to 5, I want to see that matrix in here, and you can round off to the nearest tenth. So 11.5, 13.9, 9.5. Let's make that a little bit bigger. So I just kind of rounded all these off. We already ran our test officially, but because we're not doing, we would have done this by hand for the expected counts and checked it before even running the test. But it's actually just easier to run the test, and because the calculator does it for us, to check that after the fact. All right, so all of these are greater than 5, so it checks out. N, the name of the test, which is a chi-squared test, or you can say chi-squared test of independence. Let's do the next one, phantoms. So we're doing T, which is our test statistic. So let's go back to our calculator and go to stat, test, up to chi-squared. And we did calculate before. You can either do calculate or draw. That looks like a big area. Are we expecting a big or low p-value? I'm expecting a big p-value because that's a lot is shaded. All right, so our test statistic, so this is under T, our test statistic was chi-squared equals 3.0055. Not very big. Remember, this starts at 0. And for our obtain P, so my p-value is 0.5569. So that's very high. Let's draw, and we can see how much is being shaded. 3.0055 for my test statistic, and that area is very large. P is very high for this one. So we have an easy decision. My P is high, null will fly, so we're going to fail to reject the null. And then we want to go back to what we had said for our hypotheses, and we want to say that there's not enough evidence to say that they are dependent. So let's say for our statement, actually, let's start over. I have more room here. So for our statement, we're going to say there is not sufficient evidence to support the claim, or support that. There wasn't really a claim involved. So we'll say to support that a person's place of residence is dependent on the number of years of college completed. So we're saying that it doesn't matter how many years of college, so whether you live in suburban or urban, it doesn't really have anything to do with how many years of college that you completed.